Thank, thank you very much, Hamanaka-san, for introducing me and giving me this opportunity to talk about my work. This is partly based on my joint work with my student Xiaoyue Sun from Tsinghua University and Inoue-san, Kuniba-san, Terashima-san. I think Terashima-san is here. So in the past few years, I've been interested in three-dimensional integrable systems and relations of them to supersymmetric gauge theories. So I will talk about that. So let me start. So let me begin by introducing and giving you motivation behind my work. Okay, so the main motivation is to understand connections between gauge theories and integral systems. And of course, there have been many known such connections. And integrability, as I said right here, appears in many gauge theory contexts. So I here list four famous instances where integrability appears from gauge theory. So one is gauge beta corresponds. There are many names behind this, but one famous work is the one by Nekrasov-Shachvili. And so I will not talk much about, I will not talk about that. The second example where gauge integrability appears from gauge theory is something called gauge YBE corresponds, pioneered by Spiridonov, Yamazaki-san, and others. I have done some work on it as well, and it's related actually a little bit with the present work, present talk. All right, and again, well, and then there's a four-dimensional version of Chern-Simons theory, Costello-Yamazaki-Witten theory, where integrability appears from Wilson lines in this theory. And of course, there's a famous ADS-CFT integrability and developed by many people. I will, again, not talk about ADS-CFT integrability at all. But anyway, so the point I would like to make here is that in all of these examples, in the relevant integrable systems are two-dimensional ones. Okay, so then the natural question is, what about three-dimensional integrable systems? Do they appear from gauge theories or some supersymmetric field theories? Okay, so that's the main motivation that I would like to give some answers to this question positively. So, so to begin, let me remind you of some basic facts about lattice models. So I will talk about integrable lattice models. And then first, I would like to review very briefly two-dimensional case. Okay. By the way, if you have any questions, please stop me at any moment. So I would like this to be as interactive as possible. Okay, so let's begin with reviewing two-dimensional integrable lattice models. So I'm going to consider classical spin models on square lattice in statistical mechanics. So here I have drawn a 2x3 lattice with black lines, and they are oriented lines. And then suppose it's placed on a two-dimensional torus. So I have imposed periodic boundary conditions in the vertical and the horizontal directions. Okay. Now, and I have placed spin variables, so which are represented by these circles on the edges of the lattice. Okay. Now I'm going to consider something called the vertex model, meaning, right, so these spin variables living on the edges, four of them surround a single vertex. And so each vertex is surrounded by four spins, and they interact around the vertex. And then there's an interaction energy associated to that, which I denote by this letter EIJKL, where IJKL are values of the spin variables surrounding the vertex. And then let's say they take from 1 to n different values. Okay, so EIJKL is the interaction energy associated to this local configuration of four spins. Now, in order to describe integrability of this model, this kind of spin model, it's actually convenient to use the language of quantum mechanics. So what I do is to each line, block line, they are oriented, I assign an n-dimensional local Hilbert space, which I call V. Okay, and we think of IJKL, these values of the spin variables, state vectors in this Hilbert space. By the way, do you see my pointer, or is it completely invisible? I mean,
when it's okay, it's okay. Yeah.
It's okay. It's okay.
Yeah,
okay, thank you. All right. Now, how is this related to how can we talk about integrability? To talk about it, we introduced something called the R matrix for this model. So the local Boltzmann weights, all right, so which is e to the exponential of minus e ijkl, this interaction energy divided by kb Boltzmann constant times temperature. So this is a local Boltzmann weight for that interaction. Let's call it, rename it to Rijkl. And we think of this Rijkl as ij, kl element of some matrix, or operator acting on the tensor product of V and V. Okay, I hope this is clear. So I have just defined, using the local Boltzmann weights, this operator R. Now, suppose that this operator R satisfies the famous Yang-Baxter equation, which is written just here. Okay, and then the model is actually integrable. Well, I'm skipping some important things like spectral parameters, but the main thing I want to talk about is that the Yang-Baxter equation is an important part of showing the model is integrable. Okay, and if the model is integrable, you have many commuting conserved charges, and if you're good enough, probably you can use those conserved charges and diagonalize them simultaneously and solve the partition, say, calculate the partition function analytically. Okay, so what is this Yang-Baxter equation? So it's written here, but the best way to understand the Yang-Baxter equation is a graphical way. Okay, so here I have drawn 3 lines intersecting in a plane, and let's look at the left configuration, configuration on the left-hand side. I have 3 lines, which I call line 1, 2, and 3. Line 1 is the one going from down, left bottom to right top. Okay, and then line number 2 is the one going in the horizontal direction. Okay, so if you start from left bottom and then follow along the direction of these lines, then you first encounter the intersection of line number 1 and 2, and to which I assign this operator R12. So R12 is this nothing but this operator R acting on the space V is assigned to line number 1 and line number 2. Okay, and then and this corresponds to the first factor on the left-hand side of the Yang-Baxter equation. And then if you follow the direction of these lines, then next you encounter the intersection of line number 1 and line number 3. And so this is vertex, so there's the interaction, and then there's an associated Boltzmann weight, which is represented by R13. Okay, and finally you get the intersection of line number 2 and 3, and to which you assign R23. So left-hand side of the Yang-Baxter equation is represented by this picture on the left-hand side. Okay, and then what the Yang-Baxter equation says is that if you take the configuration on the left-hand side and take one of the lines, say the line number 2, which goes horizontally, move it upward till the point that this line number 2 crosses the intersection of line number 1 and line number 3. Then you arrive at the right-hand side, configuration on the right-hand side, and Yang-Baxter equation says physics doesn't change. The partition function is invariant under this move. Okay, so that's the content of the Yang-Baxter equation. Okay, and as I said, this plus something called spectral parameters imply that the spin model we are talking about is integrable in the sense that you have you can define commuting conserved charges, and so it's a good thing. So it's a very well-known story. I'm sure many of you know about this. But the thing is, Yang-Baxter equation is hard to solve because this is a very, very over-constrained system of equations. So R has n to the 4th components because you have 4 indices Okay, but Yang-Baxter equation actually has n to the 6th components, so it's highly over-constrained. Nevertheless, there are interesting solutions and associated quantum groups and everything. And so, it's a very big field. Okay, so this is about 2 dimensions. Now, what about 3 dimensions? Now, in 3D, I would like to consider 3-dimensional cubic lattice instead of square lattice. And in my opinion, the best way to think of this cubic lattice is to think of them as consisting of intersecting planes in R3, or maybe 3 torus if you want periodic boundary conditions. Okay, so that's how I would like to think about it. Now, so here I have drawn a picture of 3 planes intersecting, and then I have drawn these black oriented lines. They are intersections of pairs of these planes, all right? And what you do is similar to what I did in 2D case. I assign to each of these black oriented lines, intersections of planes, vector space V, okay? And then I can consider local configuration of spin variables placed on these edges of this lattice. So this is a local picture of a 3-dimensional lattice around a vertex, okay? And suppose I have spin variables I, j, k, l, m, n placed on the edges of these black segments. Okay? And then I say that the interaction energy defines local bottom weight, which I call R, I, j, k, l, m, n. And think of this as a matrix element of an operator R, which acts on V tensor V tensor V. Okay? So this is very similar to 2-dimensional story. And indeed, there's a 3-dimensional analog of the Yang-Baxter equation, which goes under the name Zamolchikov tetrahedron equation. And this tetrahedron equation implies 3-dimensional integrability. Okay, so what is tetrahedron equation? So instead of 2-dimensional case where you had 3 lines intersecting in a plane, here in the tetrahedron equation, you have 4 planes intersecting in 3-dimensional space. And these 4 planes, well, they intersect in a way that they bound a tetrahedron. So here you have, on the left-hand side, you have a tetrahedron. You have 4 planes intersecting, okay? And inside, surrounded by, well, they surround a tetrahedron, okay? And I name these 4 planes plane number 1, 2, 3, and 4. And then at the intersection of plane number 1, 2, and 3, I have this associated R matrix R1 to 3, which represents the local bottom weight here, and so on and so forth, okay? So left-hand side of this picture represents the left-hand side of the tetrahedron equation. Now, the content of the tetrahedron equation is that you take one of the 4 planes, say the one on top, okay, which goes horizontally, and you pull it down, and then you arrive at the another configuration of 4 planes, 4 intersecting planes, which is drawn on the right-hand side, okay? And the tetrahedron equation says the partition function of the, what you calculate in the respective side, well, they are equal. So that's the tetrahedron equation, and that implies the integrability of the 3-dimensional lattice model, okay? So, so this is a fairly natural generalization of the Yang-Baxter equation. So now, what is the state of the art about in the study of tetrahedron equation? So, tetrahedron equation, I would like to stress, it has a relatively long history because it was introduced by Zamolchikov in 1980, and that's, if you think about it, that's actually before the famous BPZ paper on CFT. Okay, so it has actually longer history than modern study of CFTs, 2D CFTs. But it's also fair to say it's far less developed than Yang-Baxter equation. And as far as I know, there's only one book written by Kuniba-san, which appeared 2 years ago on the subject. Okay, so And the primary reason why it's not so developed compared to Yang-Baxter equation is that it's even more complicated than the Yang-Baxter equation if you count the number of components and constraints. Okay, it's very highly over-constrained, and then nevertheless, Zamochikov could write down non-trivial solutions in his original papers, and by according to Baxter, by what appears to be an extraordinary feat of intuition. So it sounds like a miracle that this equation has non-trivial solutions, but it does. Okay. But I would also like to emphasize that even though there hasn't been much progress, there are some important progresses, but not much compared to Yang-Baxter equation. But the tetrahedron equation is certainly interesting and important. And primary reason I would say is because we actually live in three-dimensional space, so it should make sense for us to study three-dimensional integrable lattice models. Okay, and then there have actually been recent developments, so which I'm involved in, and I would like to talk about mainly the second item, but briefly on the first item as well. So one is that a realization that some solutions of the tetrahedron equations actually come from something called class algebras, and they can be related to 3D supersymmetric gauge theories. So this is my work with Xiaoyue Sun and also IKT Inoue Kuniba Terashima-san. And we have done some work together. And there are some important work by Russian Ukrainian people, which is also part of the motivations for our work. So I will probably, well, it depends on how much time I will have, but I will briefly talk about this work. Yeah, I may not have so much time because I am
Yagi-san, it's flexible, so no problem to extend.
Is it? Okay.
Yeah.
All right. I'm not sure if people's schedules are flexible, but okay, thank you. But anyway, so I will be very brief about this work because I know Inoue-san and Kuniba-san, they have talked about this multiple times already. So some of you, I'm sure some of you have heard about this already. So I would like to spend more time on the second item, which is that I could actually construct solutions of the tetrahedron equation using duality, equivalence of two-dimensional supersymmetric gauge theories. Okay. And there's actually
I would like to confirm that this 2D is a spatial 2D or time and space?
Well, I was in probably Euclidean space-time, but this is it's space-time dimension.
Totally, okay.
Total, yeah.
Okay.
It could be Minkowskian or Euclidean, maybe it doesn't matter. Yes, so you can say it's 1 + 1D.
Okay, so in that sense, our universe is 4D.
Yes.
Okay, right. Okay. Thank you. Okay.
Also, I have proposed that some important solutions of tetrahedron equation actually appear as the partition function of certain brain system in M theory. I'm not going to talk about it, but it might be interesting to look for some connections between this brain construction and other constructions. So this is sort of the end of introduction section. So if you have any questions, this is a good point to ask. And if there's no question, I would just like to move on to talk about or outline, give you an outline of the first construction, plus the algebra construction. But I'll be very brief. So, but I'll be happy to answer or explain more afterwards. Okay. So let me move on to explain the first construction using cluster algebras. Right. So as I said, this is a joint work with Sun, Inoue-san, Kuniba-san, Terashima-san. Okay. So Yeah. All right. So what is this about? So we are going to use something called wiring diagrams and quivers. So there's a technical definition of wiring diagrams, but for the purpose of this talk, you can just think of them as some curves, intersecting curves in a plane. Okay, just like this one. So these the blue curves here are something called wires. So in the first diagram, you have two wires intersecting. Okay, and when you're given this kind of wiring diagram, what we do is to assign a quiver to it. And there are actually different ways of assigning a quiver to wiring diagrams, and they lead to different solutions of the tetrahedron equation. But in this talk, I will just focus on one example, which is called the square quiver, okay, which leads to a particular solution. So what I do is I place these circles, these vertices, okay, on the segment of these wires around each intersection of wires. And then I connect them by arrows. Then you get this picture here. Okay. So it's a square of arrows connecting vertices. So that's why we call it a square quiver associated to this wiring diagram. So this is the simplest example. So let me introduce another wire and make a little bit more complicated configuration of wires. So here in the next example, you have three wires and they intersect like this, okay? So, and then according to the rule I just explained, I can assign a quiver. So quiver, by the way, is just a directed graph. So you have vertices connected by arrows. So that's what quiver is. So here, the associated quiver is this one, okay? So around each vertex, you have square of arrows connecting vertices. I hope this is clear. Now, the key point is, there's something called Yang-Baxter move or braid move you can apply to a configuration of wires, okay? Which goes like this. So suppose you have wire A and B and C making this configuration, and you apply this braid move, beta ABC, let's call it beta ABC, then this diagram becomes the diagram on the right. So what I did was to deform the middle, the wire B, and move the middle part upward, okay? Then what happens to the associated quivers? Well, quiver transforms from one quiver to another quiver, okay? And then what I found with Xiaoyue was that this transformation, well, actually, this has been known from works on gauge YBE correspondence, but these two quivers are related by actually a sequence of mutations. So mutation is some kind of operation which you can apply to a quiver, and that changes quiver from one quiver to another quiver. Okay, so I don't really explain the definition of mutations here, but I can explain it later if there are questions. But let me just move on. But the point is, the two quivers related to two wiring diagrams connected by braid move, they are related by a sequence of mutations. Okay, so you can just check it. Now, so from quivers, given quivers, actually there's a way to go to quantum mechanical system using something called the theory of quantum cluster algebras developed by Fock and Goncharov. Okay, so here as I said, I'll be very brief about this cluster algebra construction. So I just say that there is a well-known way to construct quantum mechanical system given a quiver. All right, so given a quiver Q, there is a quantum mechanical system. By that, I mean you have Hilbert space and the non-commutative observables, all right, which I call Fock-Goncharov system of Q. And this quantum mechanical system is nice in the sense that if you're given two quivers which are related by mutations, then the corresponding Fock-Goncharov quantum mechanical systems are isomorphic, equivalent in the sense that there's a unitary operator from one system to another system. Okay. And then, so that's what Fock-Goncharov's quantum mechanical system is. But let's apply this map from quivers to quantum mechanical system to the previous example, where you have two wiring diagrams with three wires related by this braid move. Okay, so because braid move induces a sequence of mutations, which means that the corresponding quantum mechanical systems associated to quivers assigned to each of these diagrams, they are related by a product of some unitary operators. Okay, so this braid move actually induces an isomorphism of two Hilbert spaces of two quantum mechanical systems, which I call R. Okay? And this R is going to be the R matrix. Okay, which satisfies the tetrahedron equation. Now, why is this related to tetrahedron equation? The reason is actually there is a very interesting loop of braid moves you can you can consider for wiring diagrams with four wires. Okay, so which goes like this. So here on the top left corner, I have some diagram of wires, four wires intersecting in a plane, right? And then I name these wires wire number 1, 2, 3, 4 from bottom to top on the left end. Okay, and then what you can do is you can apply this sequence of braid moves, 8 braid moves, actually 4 braid moves, and then 4 inverse braid moves. And what happens is that this wiring diagram transforms, and then finally it comes back to the original wiring diagram. Okay. So if you think about it, so to each wiring diagram, there's an associated quiver. And then to each quiver, there's an associated quantum mechanical system. And then you have applied 8 braid moves, and it comes back. And then according to what I said, there are 8 unitary operators. And if you multiply them, okay, it comes, well, it's going to be some unitary operator acting on the Hilbert space of the first quantum mechanical system associated to quiver on the top left corner. Okay, so the existence of this loop of braid moves actually shows that this combination of unitary operators corresponding to these braid moves is an endomorphism of the Hilbert space of this quantum mechanical system associated to the first diagram. Okay, I hope this is clear. I'm explaining it clearly. And then, so you can go on and try to calculate what this operator is. And then if you actually do that, I mean, you don't really have to actually calculate this, but there's some abstract argument and theorems which you can employ here. And then you can actually show that this operator turns out to be equal to 1. Okay. So this operator, this product of 8 R's is equal to the identity operator acting on this Hilbert space. And then you notice that that's actually equivalent to the tetrahedron equation. If you just have to move these R inverses to the right-hand side, and you exactly obtain the tetrahedron equation. And in this way, you can construct the operator R, which solves the tetrahedron equation. So that's what I did with my first work with Xiaoyu Sum. Okay, and then you can actually calculate the matrix element of this R. So this R is some unitary operator. Okay, like I said in quantum mechanics. So you can just calculate the matrix element. And if you do that, it turns out that it's actually coincides with the partition function of a certain 3-dimensional n equals to supersymmetric gauge theory on 3 sphere. Okay. Well, I don't write down the details, but I can just say this in words. But this matrix element of R can be written in terms of integrals of non-compact quantum logarithms. Okay, and then that appears exactly in the localization calculation of 3-dimensional supersymmetric gauge theory on S3. Okay, so somehow this is what we found. So we have constructed a solution of solution R of the tetrahedron equation, and that turns out to be 3D partition function of three-dimensional gauge theory. Right? And then, so you have a tetrahedron equation. So tetrahedron equation takes the form R is equal to R. Okay. And as I said, each R corresponds to the partition function of one theory. Okay. So what is then R, product of R's? That's actually has the interpretation of the partition function on S3 of a big theory constructed by combining four smaller three-dimensional theories. Okay. So the tetrahedron equation, each side represents the partition function of some big three-dimensional gauge theory. And the two sides actually represent seemingly different theories. Actually, I think they are different theories, but they are actually equivalent in the infrared at low energies. They float under RG flow to the same fixed point. So tetrahedron equation turns out to be the statement that these two big theories, 3D theories, representing the two sides of the tetrahedron equation, are actually dual to each other. Okay, so that's the main that's the conclusion we have achieved in my first work. So in the subsequent work with Inoue-san, Kuniba-san, and Terashima-san, we have further developed this direction, and they have done some important work, and we have shown that this by realizing this quantum mechanical system using something simpler QYL algebras, then we can actually reproduce many of the important previously known solutions of the tetrahedron equation. So somehow all those previously known solutions can be all accommodated in this approach. Okay? And if you want to know more about this, I would recommend you to look at slides or videos of talks by Inoue-san and Kuniba-san. Okay. So yeah, as I said, this is very brief. So I'll be happy to answer questions and explain more. But now, and if you don't have any questions, I would like to actually explain to you another construction of solutions of the tetrahedron equation, which is a new work of mine. Okay, and that's related to two-dimensional supersymmetric gauge theories instead of three-dimensional ones. Okay, right. So yeah, if there's no questions, so let me move on. So actually, I explained this in one of the workshops. So some people might have seen this before. So, but please bear with me. So this is my newer work, tetrahedron equation from 2D duality. All right. So this work is actually related to this gauge YBE correspondence, which I briefly mentioned at the beginning of my talk, and actually is inspired by this. So I have to begin with explaining what gauge YBE correspondence was. Okay, so there are different versions of gauge YBE correspondence, different degrees of complexity, but I'll talk about the simplest case. Okay, so there's something called brain box model in gauge theory and string theory. So it was introduced by Hanani and Zaffaroni a while ago, 98. And if you know a little bit about brain constructions of gauge theory, this slide makes a lot of sense, but otherwise, please just, it's gonna be still okay. Okay, but I consider 10-dimensional theory, string theory, actually type 2B string theory, and I take the 10-dimensional space-time to be just R10, but I divide this 10-dimensional space-time in this form, okay, R4, and here 0, 1, 2, 3 means that the coordinates are x0, x1, x2, and x3. Okay, so you have R4. You have R2 in the 4, 5, x4, and x5 direction, R2 in 6, 7 direction, R2 in 8, 9 directions. Okay, and in string theory, there are extended solitonic objects called branes, and there are different kinds of branes, but in this type 2B string theory, there are particularly two kinds of branes called D5 branes and NS5 branes. So there are some 6-dimensional objects. D5 means 5-dimensional space directions and 1 time direction in this word volume of branes. So what I do is I take n of them and stack them together, and I place n of the n D5 branes inside the 10-dimensional space-time and say that they extend in R4, 0, 1, 2, 3 direction and R2, 4, 5 directions. But let's say that they sit at points which are the origins of R2, 6, 7, 8, 9 directions. Okay. And to this configuration of D5 branes, I introduce furthermore NS5 branes. And there are two different NS5 branes differing in the directions in which they extend. All right. So one type of NS5 branes, which I call NS5XL, L runs over integers. Well, they extend in the same R4, 0, 1, 2, 3 directions, but they are placed at extend in along X5 directions in the R2, 4, 5, okay, and X7 directions in the R2, 6, 7, okay, and supported at the origin in the 8, 9 direction. Okay, so that's NS5XL because it goes in. Well, that's what it is. Okay. I also introduced NS5YM. M also runs over integers. These branes, they differ from NS5X type branes in the direction in which they extend in the R2, 4, 5 and R2, 6, 7 directions. Okay. So, but the point of introducing these is that these NS5s make a square lattice in R2, 4, 5. Okay. So you have D5 branes and then NS5's branes intersect this stack of D5 branes. In a way, it makes a square lattice. And so this is what I want. And this is the square lattice on which an integrable lattice model emerges. Okay, so, and then, well, so you have this brane configuration. If you go to low energy limit, then the dynamics of D5 branes in this configuration is actually described by a 4-dimensional supersymmetric gauge theory whose matter and gauge contents are specified by encoded in this quiver. Okay, and well, so here I have drawn a quiver. Let me explain what I mean by this. So here's this quiver. Each vertex of a quiver actually represents an SUN gauge group. N is the number of D5 branes. And each arrow between two vertices, say vertex A and B, okay, so it represents some matter field, which is in the fundamental representation, in the vector representation under B, under SUN gauge group at vertex B, but in the dual representation under the SUN gauge group at vertex A, okay? Now, I have many SUN gauge groups, and they can be labeled by two integers, L and M, okay? Because they make this lattice structure, okay? And SUN L, M, this gauge group actually arises from the part of D5 branes containing this integral point LM in the R245. Okay, so you have square piece of D5 branes which can move up and down, fluctuate, and that creates this SUN L, M gauge group. Okay, and there is something called U1R symmetry, which comes from the rotational symmetry in the R2, 8, 9 directions. All right, all of these branes are located at the origin, so there's this rotational symmetry, which gives rise to this U1R symmetry. And there are a lot of global symmetries called flavor symmetries. And okay, so that's what the theory is. Okay. Now, the point is, if you look at this quiver, it just looks like some spin model on a square lattice, where spins are these circles like before. And then what are these arrows? These arrows, you can think of them as some interaction between pairs of spins. Okay. And you clearly see some lattice structure. And you can talk about the unit cell of this model or this quiver. All right. So that's just this. So if you have 4 spin sites and then you draw this triangle of arrows, then this is like a unit cell. By repeatedly concatenating this infinitely many copies of this unit cell, you can get this quiver. Okay. Okay. So this quiver somehow looks like a spin model, and indeed it actually defines an integrable lattice model. So, and that's called gauge YB corresponds. So this unit cell, right? Actually, so you have 3 arrows. So this unit cell itself represents a 4-dimensional supersymmetric gauge theory with 3 matter fields, matter multiplets. Okay. And these matter fields, matter multiplets, this theory can be, some copies of this theory can be combined together to form a bigger theory like brain box model theory. All right. But this unit cell theory actually solves the Yang-Baxter equation in the following sense. So I have drawn the same picture, almost the same picture as before. I have actually 3 lines intersecting here in one way or another way, and the equivalence between them is the Yang-Baxter equation. But here, spin variables are located not on the edges of lattice lines, but rather they are located on the faces of the lattice. Okay, so you have spin variables connected by these lines. Connected by these blue arrows. Okay, and the left-hand side represents the left-hand side of the Yang-Baxter equation, where the R matrix is represented by this 4-dimensional theory constructed from 3 arrows. Okay, so you have combined these theories and you get this picture, and you can do something similar on the right-hand side. Okay, so then you get 2 4-dimensional theories. Each of them are obtained from 3 copies of this unit cell theory. Now, what's amazing is that these 2 theories actually are dual to each other. So they are at low energies, they float to the same fixed point. At low energies, they exactly describe the same physics. To see that, you notice that, so here you have pairs of arrows going in the opposite direction between the same pair of gauge groups. And you can actually cancel them because you can turn on some potential term which give masses to each of these arrows. And so that makes it massive. And in low energy, so because they are massive at low energy, they are gone. Okay, so you can actually cancel these pairs, about these pairs of arrows. And then you can actually cancel some arrows between which are common on the on both sides. Okay, and then move some arrows from left to right. Then this equation, Yang-Baxter equation, can be written in this form. And this is actually exactly the relation between one quiver and mutated quiver, and that turns out to describe Seibach duality, this infrared duality of 2 theories. Okay. So Yang-Baxter equation is promoted here. It's a statement about the duality between 2 different 4-dimensional theories. So it's a very powerful statement, and in order to obtain some solutions, ordinary solutions of the Yang-Baxter equation, you can just calculate some quantity in each theory, which are protected under the RG flow. Okay. Then one example is something called supersymmetric index. What you do is you take each theory, each 4-dimensional theory, place them on S1 times S3. You calculate the partition function. Okay. And then this quantity turned out to be RG invariant. So you can calculate this quantity in the infrared, but that gives you the that you can calculate this quantity in the ultraviolet, but that gives you this the same quantity in the infrared. But in the infrared, two theories on this equation exactly describe the same physics. So these two quantities you calculate in the ultraviolet, they must be equal. Okay, and in this way you can obtain some numerical solution of the Yang-Box equation. So this is the gauge YB corresponds. Okay, so I'm just reviewing this now. Let me see how much time do I have. I only have 15 minutes, so I will skip a little bit. But in this slide, the point of this slide I'm showing right now is to explain to you there's a good reason to believe expect that why you obtain Yang-Box equation from this construction. The point is actually in this construction, a brain construction, you can show or argue that theory describing the dynamics of DeFi brains is a 6-dimensional theory which have some topological invariance in R245 direction and things depend homomorphically on the first 0, 1, 2, 3 direction. Okay, and NS5 brains create line operators in this topological field theory on sigma. Okay, so you can insert topological line defects, like 3 of them, like the left-hand side of the Yang-Box equation. But things are topological, so you can move these lines around so that, and you can try to go from one configuration topological line defect to another configuration. Okay, and that corresponds to going from the left-hand side to the right-hand side of the Yang-Box equation. But you may say that left-hand side and right-hand side of the Yang-Box equation have different topologies of 3 lines, and that's correct. But actually, there's an addition in this theory. There's an additional direction which comes from this S1 times S3, and you can show that in some dual frame, these 3 topological lines sit at different points in this extra direction. So there's nothing singular going on when you go from left-hand side to the right-hand side of the Yang-Box equation, and you can smoothly move one line on the left-hand side of the Yang-Box equation and pass the intersection of 2 lines, and you obtain the right-hand side. And so this is a reasoning behind the appearance of the Yang-Box equation from this brain construction. But anyway, so all of this was understood back in 2015. I explained this. But in this work, I thought about, well, wait a minute. So there's actually, why don't we apply the same reasoning to higher dimensional integrable systems, namely 3-dimensional lattice models? So back in 2015, I had this idea. All right. So there's actually a higher dimensional analog of this brain construction, which goes under the name 3D brain box model. Okay. So it's very simple. Well, instead of type 2B string theory, I consider type 2A string theory. Well, details doesn't matter. But the thing is, instead of D5 brains, I can consider D4 brains, which extend in this direction. Now here, you notice there's R3 in 2, 3, 5, X2, X3, X4, sorry, X2, X3, X4 directions, okay? And then I can introduce NS5 brains in various directions. They are supported on planes in the 2, 3, 4 directions, and they make actually a 3-dimensional lattice, cubic lattice, like I explained before, okay? And then these people, or in the original 3D brain box model, they explain what this configuration of brains leads to. Well, it leads to actually produces a 2-dimensional n equals 0, 2 supersymmetric gauge theory, which is also described by a quiver, but this quiver has a 3-dimensional structure, okay? And it looks like this. So this quiver can be drawn in this X2, 3, 4 directions. and you have a lot of vertices and connected by arrows. Now, here there are two different arrows, either blue solid arrows or dashed red arrows. Okay, and they just describe different kinds of matter multiplets. Okay? So here, each circle, each vertex is a UN gauge group. So you have a lot of gauge groups, and they are at lattice integral points on R3. And solid arrows are something called bifundamental chiral multiplets. Dashed arrows are bifundamental Fermi multiplets. Okay, so it's a little bit complicated, but not so much. Okay. And then, so you see some three-dimensional lattice structure. And my idea was to think of this as some lattice model and try to apply the same reasoning as before in the two-dimensional case and show that this gives you an integrable lattice model. Okay, so and what is a unit cell for this lattice? Well, the most natural definition of unit cell is just this one. So you have a cube, okay, and then you have arrows, blue arrows and red arrows connecting the vertices of cube in this manner. You just take many copies of this cube and concatenate them, all right, and then you can create this more complicated, bigger quiver. Okay, so I thought, well, you just take this unit cell theory and plug this into the tetrahedron equation and show that tetrahedron equation holds. So this solves the tetrahedron equation. So that was my idea back in 2015. Okay, and here in this slide, I explain why the same argument as in two-dimensional case should apply. There's actually a structure of three-dimensional three-dimensional topological quantum field theory in this R3, 2, 3, 4 directions. And these NS5 brains, well, I lifted everything to M theory, but those planes become topological defect surfaces, and then you can move around these topological surface defects, and then you can go from one side of the tetrahedron equation to another side of the tetrahedron equation. So it seemed like everything that I said about two-dimensional gauge by B corresponds should work here. And I tried very hard, but I found that in the end, this is not correct. It doesn't, this unit cell theory doesn't solve the tetrahedron equation. So that was my conclusion back in 2015. And until like very recently, I had no idea why this doesn't work. Okay, so this puzzle was resolved in my latest work, in which I would like to explain a bit. Okay, and I don't, disclaimer is that I don't fully understand why this works, but it does work. Okay, so the point was to note that there's more than one way of defining choosing a unit cell for a given lattice system. Okay, so here I have chosen the first picture as a unit cell. This is actually very natural unit cell from the point of view of brain construction. Okay, but there's another way to choose a unit cell, which actually is this one. It's which I call a slanted unit cell, okay, or oblique unit cell. So here, what I do is the following. So you have two cubes. I consider two cubes, and instead of taking this unit cell on the left, I take the upper face of cube and shift it by one unit to one direction. And instead, I consider this slanted cube as a unit cell. All right, you could as well use this as a unit cell and concatenate them and construct a bigger quiver, which is the original quiver for this three-dimensional brain box model. Okay. And by some change of variables, you can also represent this unit cell in the manner in the way I draw on the right-hand side. And then it turns out that if I plug this into the tetrahedron equation, then magically this solves the tetrahedron equation. That's what you find. Okay. But what really is this? So by this oblique unit cell, this is really a two-dimensional n equals 0, 2 supersymmetric gauge theory constructed from 1, 2, 3, 4 chiral multiplets and 1, 2, 3 Fermi multiplets, and you have a lot of UN symmetries. Okay, and there are some parameters you can actually introduce here, which control the charges on the U1R symmetry. And so there are actually 3 parameters you can introduce for this theory, and these parameters play the role of spectral parameters. But now, what you find when you plug this into the tetrahedron equation is the following. So here, so this is this picture I show here is another form of tetrahedron equation, which is appropriate for the theory I'm considering. So I'm considering something called an interaction round the cube model, where the spin variables are located on the inside the say regions of 3-dimensional lattice. Okay, which are actually vertices of the dual 3-dimensional lattice. But anyway, so in the type of model which naturally arises from this 3-dimensional brain box model, that's called interaction round the cube model, then this picture represents the tetrahedron equation. Okay, so here you have a lot of vertices, square vertices, and the round vertex D. To each vertex, you have some spin variable. Okay, and then the round vertex means that the spin variable located there, it's summed over. Okay, and each cube represents some R matrix or boson weight. And so this total picture is something called the rhombic dodecahedron. So the tetrahedron equation says there are 2 ways of decomposing rhombic dodecahedron into 4 cubes. And then to each cube, you have local boson weight. But then these 2 ways of decomposing gives you the same answer. So that's the content of the tetrahedron equation in this form. Okay, but now I know that each cube represents this unit cell theory. I plug that in, and then sum over this spin variable D here. Actually, you can think of it as gauging some UN global symmetry. Okay, you can construct one very complicated 2-dimensional n equals 0, 2 theory on the left-hand side according to this way of gluing for unit cell theory. Or you can glue 4 unit cell theory in a different way according to the right-hand side of the tetrahedron equation. Okay, and then if the tetrahedron equation is satisfied by this unit cell theory, then you should find the equivalence between these 2 theories. So that's going to be the statement of the tetrahedron equation solved by this unit cell theory. Okay, and you can just check that this is actually true. And this is true because of something called 0,2 triality. Okay, so you can use some relations like the one on the left, one on the right on top line. So for example, if you have 2 matter multiplets, one is chiral multiplet and another one is Fermi multiplet with R charges R and 1 minus R, like this, then you can turn on mass terms between them and they are gone in the infrared. So you can cancel these 2 arrows. And then there's a general relation in general property about 2-dimensional 0,2 model, which says that Fermi multiplet can be the direction of Fermi multiplet. All right, dash arrow can be reversed. And if you use these relations, then the tetrahedron equation for this unit cell theory can be simplified to this picture in the middle. Okay, and so each side of this picture represents some 2-dimensional 0,2 theory, and they are actually known to be dual to each other. But like I said, it's there's actually triality. There's a triple of theories which are dual to each other in the infrared, and two of them are these. Okay, so there's actually another theory which is equivalent to the further equivalent to these two theories, which I'm not showing here. Okay, so so amazingly, this unit cell theory does solve the tetrahedron equation. Okay, so that's what you find. And then you can go on to write down ordinary solutions of the tetrahedron equation. So here I'm saying that the tetrahedron equation is solved, is promoted to a duality between two-dimensional gauge theories. But in each of these two-dimensional gauge theories, you can calculate some quantity like partition function on the torus. Then the partition function on the torus will give you an ordinary numerical solution of the tetrahedron equation. So that's how you can obtain solutions of the tetrahedron equation from here. Okay, so I'm almost using up time, but Hamanaka said
No problem. No problem.
yeah, no problem. Okay, so let me yeah, I won't do much. I won't need many more minutes, but just a little bit. Let me go on just a little bit. Okay, but anyway, so from now on, what I want to now you would like to do is to actually calculate some quantity in these theories. Okay, and then that will give you ordinary solutions of the tetrahedron equation. But there's a catch. All right, so there's a caveat. Triality of these two-dimensional theories require cancellation of something called U1 gauge anomalies. And there's a way to cancel. So the theories I described before using these quivers on, okay, actually those theories suffer from this U1 gauge anomaly, and there's no way of canceling U1 gauge anomalies by further introducing something called determinant fermion multiplets, or something called generalized Green-Schwarz mechanism. Okay, so you can, in principle, do that. And if you start from brane construction, this Green-Schwarz mechanism should be automatically implemented, and this gauge anomaly is automatically canceled because brane construction is anomaly free. But unfortunately, formula for, say, something like partition function, supersymmetric partition function on the torus with this Green-Schwarz mechanism implemented is not known in, okay, so in this case. So I can't use any known formula to write down some nice quantity to write down a solution of the tetrahedron equation. But there are some ways to avoid this problem. So one is to reduce this brain box model, which is a two-dimensional gauge theory, to one dimensions. Then in one dimension, there is no this kind of anomaly. So this anomaly actually goes away if you dimensionally reduce this two-dimensional theory to one-dimensional theory. And in one dimension, so now you have some supersymmetric quantum mechanics, and you can calculate the Witten index, trace of -1 to f, with some additional things thrown in the trace of the resulting supersymmetric quantum mechanics. And if you do that, you obtain a solution of the tetrahedron equation. And then I can actually use some formula for this Witten index, which was worked out by these people. Okay, and then you can write down a solution. So and then what you obtain is the following. So this is going to give you something like an Ising model. So W represents a weight, bottom weight. Okay, so if you have two vertices which correspond to two UN gauge UN groups, okay, and an arrow between them, and this arrow represents a chiral multiplet charged under A and B, UNA and UNB, and suppose this multiplet has R charge under U1R. Okay, and that's equal to S. Okay, so this is a U1R charge. Then to this So as I said, A and B, these are UN gauge groups, but you can think of them as spin sites, where spin variables are A1, A2 up to AN at site A. And similarly, you have B1, B2 up to BN at site B. And these are circle valued in a unit circle. Okay. And then I define this function phi of z, which is just this one written here. And then this is the Boltzmann weight for interaction between spin variables at site A and B connected by this arrow with charge S. Okay. And similarly, if you have some Fermi multiplet between UN gauge group A and UN gauge group B, then that's another kind of interaction between spin site A and spin site B. And here's the Boltzmann weight. So what you do is you multiply these Boltzmann weight. They are just Boltzmann weights for interactions between spins. Okay, and then finally you sum over all spin configurations, which means that in this case spin variables are continuous. Summation becomes integral, and you integrate over these spin variables AIs and BIs and so on using this measure. Okay. And then there are many poles in which you have to avoid and then pick up and so on. But the prescription is to pick up poles from this kind of factor W of arrow going from B to A, okay? And so on and so forth. But anyway, so this is a concrete model, concrete way to calculate a partition function. And you can show that this leads to an integrable lattice model. So that's one way to extract some solution of the tetrahedron equation. And another way is to actually consider a model which is some variant of this 0,2 brain box model, but which has half as many supercharges, and gauge groups are not UN but SO2Ns. Okay, but there is actually a similar triality between triplet of this kind of theory found by similar people, Gukov and Pei and Putrov. Okay, and combinatorial features of this triality for these 0,1 supersymmetric theories are almost identical to the 0,2 theory, okay, to the case of the original triality for 0,2 theories. But unlike the 0,2 case, for 0,1 triality, there's no issue of this gauge anomaly. There's no anomaly. They show that in this paper. And then using this kind of variant of brain box model, 3D brain box model, you can also construct solution of the tetrahedron equation. Our argument works very similarly. And you can write down, and then you can calculate the partition function of this kind of theory, which you obtain from, using some localization formula. Okay, and then you can, that gives you another solution of the tetrahedron equation. Here, the solution Boltzmann weight can be written in terms of theta function. Okay, and so here's the Boltzmann weight. And then here's the integration measure. But for 0,1 case, there's no continuous parameter you can assign to these multiplets. So there was a parameter S before. For 0,1 case, there's no such a parameter because there's no U1R symmetry for 0,1 theories. So spectral parameters are unfortunately missing. But nevertheless, you can still construct a solution of the tetrahedron equation by calculating the partition function of 0,1 theories. Okay? So that's another way of constructing solution of tetrahedron equation. So, so that's what I wanted to explain today. Okay? So I would like to make some comments and conclude this talk. So, and I give you some outlook. So the main message I wanted to convey today is that tetrahedron equation is very important. It's a three-dimensional analog of Yang-Box equation that underlies 3D integrability. It's important, definitely important, but I would say still not very well understood. And then I explained to you solutions of this equation appears from cluster algebras, and then solutions constructed from cluster algebras are related to partition functions of 3D n equals to gauge theories, supersymmetric gauge theories on S3. Another way of constructing solutions is to use dualities of two-dimensional supersymmetric gauge theories, which I explained. And then there's actually brain construction of some solutions, which I didn't talk about. But now, where can we go from here? So there are many questions I would like to see no answers of. So one is, so there are different constructions of solutions of the tetrahedron equation. How are they related? So that's one question I would like to answer. Okay, and then can we develop these constructions more to construct more solutions? And I would say the answer is definitely yes for, say, this brain box model construction, because this brain box model, which I explained here, is actually a simplest of a much bigger class of brain constructions, which is known as brain brick models. So there's recent work by Sebastian Franco and his collaborators called brain box models, and it's related to Calabi-Yau 4 and so on. And I don't know much about it, but I'll be interested in learning that and then apply their tools to construct more solutions. I think that's promising direction. And I'm saying this because the 2D version of my story, gauge YB corresponds, I only explained the simplest case of gauge YB corresponds related to 2D brain box model. But that's the simplest member of a family of theories, which known as brain tiling models. Okay? And then you can use more different members of brain tiling models to construct more solutions of Yang-Box equation. So I would expect using different members of brain box models, you can construct more solutions of the tetrahedron equation. Okay. And another important question is, here, all models I talked about in this talk, their spin variables take continuous values. So question is, how can we take any, say, certain limit of some parameters to obtain discrete spin variables, models with discrete spin variables, which might be more interesting for experimental realization, for example. So I'm saying this also because in the case of gauge YB correspondence, there's some known procedure to go from continuous spin variable models to discrete spin variable models. So you start from solution of the Yang-Box equation with continuous spin variables. You take certain root of unity limit in certain parameter, you obtain solutions of the Yang-Box equation with discrete spin variables. And that way you can actually reproduce a Chiral-Potts model and Ising model, and actually many known solutions of the Yang-Box equation. They are actually unified into this continuous spin variable R matrix. And so in this sense, this continuous spin R matrix for Yang-Box equation is called the master solution. So I hope something similar can be done for solutions of the tetrahedron equation. And so this is another interesting direction. And of course, we are, not everyone, but I'm a physicist. I would be interested in what physical things I can say about three-dimensional statistical mechanics in general from here. Okay, and finally, there's this work in progress with my student postdocs. Okay, and so I said before that solutions of the tetrahedron equation constructed from class algebras are S3 partition functions on S3 of three-dimensional n equals 2 supersymmetric gauge theories. Supersymmetric gauge theories can be actually constructed from some three manifolds. So you start from six-dimensional theory, you compactify that six-dimensional theory on three manifolds, and you are left with three-dimensional theory, which turns out to be three-dimensional n equals 2 supersymmetric gauge theory. So there's actually this relation between 3D gauge theories and three manifolds, which is known as a 3D correspondence. Okay. On the other hand, I have told you that 3D gauge theories, this kind of 3D gauge theories can be used to produce solutions of the tetrahedron equation. So now we see that there must be connection between three manifolds, actually 3D hyperbolic geometry should be related to tetrahedron equation in this way. Okay. In my work in progress, we are looking into this direction. So I think I can say more once we are almost done with this. So I can, if you're interested, you can ask me questions about this. So, okay, thank you very much. So that's all I wanted to say today.
Okay, thank you very much for very interesting talks.